Sorry about that. Okay, I think we are recording, so we can begin. Welcome everyone, thanks for joining. Tonight we are going to finish up learning unit 6, and we are going to cover the normal distribution. And the normal distribution, not only is it a very widely used distribution in the real world, it's probably the most used distribution in the real world. But it's also a distribution you need to familiarize yourself with because it carries over into learning unit 7 and learning unit 8. So it's very, very important that you have a good understanding about the normal distribution, how to get the probabilities, and if you are asked a question about a normal distribution, and you kind of understand exactly what they're asking for and how to use the table that's given to you to derive those probabilities. Okay, so let me share my screen. Just give me a second. Okay, if you can't see my screen, please let me know. On my screen, I'm showing you the table. Now this is in the back of your textbook. So if you have the 6th edition, it's on page 578. And if you have the 5th edition, then it's on page 506. So you should see this table in the appendix. It's your first table, table 1. All right, so get to it. And we're gonna use it. For now, you can just follow along what I'm showing you on the screen. All right. So let me go to my whiteboard. And here we go. All right. So let's forget about probabilities and anything sort of like mathematical in a sense. And we're not gonna connect this to a real world application right now. For now, what I want to focus on is I want you to be able to understand when I talk about an area, how to get that area from this table. All right, so let me give you an idea of what I'm talking about. So let's say if I want you to use this table to find the area. Oops. So let me just change the size of the text. Be better. All right. Really? Okay. So I want the area of Z between 0 and 1.6. All right. Now, what do I mean by that? So if you look at the graph on the left, okay, that graph on the left is a bell-shaped curve. So I'm going to sketch that curve here. All right, it's going to be a rough sketch. It's not going to be as neat as the diagram that you see on the left. So center around here. That. And the center, where it's peaked, is 0. So I'm drawing the curve that you see on the top left on your textbook, all right, on that page. Now, what that graph tells you is for any value on the horizontal axis. So your horizontal axis, so that means this axis here, okay? This goes to infinity. And on the left, it goes to minus, sorry, last 1 second. Let me just put my charger on. I think my screen's just going into sleep mode and I don't want it to. Sorry. That should be better. Okay, so the horizontal axis goes from minus infinity all the way to positive infinity. All right. Now, when I'm asking for the area between 0 and 1.6, what I'm asking for is the area under this curve. So here's 1.6 on the horizontal axis, right? And all the values on this horizontal axis are your Z values, right? So here, this is Z is equal to 1.6. Here, this is Z is equal to 0. So if I want the area between 0 and 1.6, so there's 0, there's 1.6. I want the area between this.
Hi, sir.
Yeah,
I can't see your screen.
it stopped sharing.
Yeah,
Okay,
same here.
thanks for letting me know. Can you see it?
Yes, much better.
Cool, great. So the area between 0 and 1.6, so here's 1.6 on the horizontal axis, here's 0 on the horizontal axis. If I want the area between those two, then what I'm asking for is this area here under this curve. Now, what this table on the left does is it gives you that area. So any area between 0 and some specified Z value, in our case, the specified Z value is 1.6, right? This is the Z value, 1.6. So if you want the area from 0 to Z equals to 1.6, you use the margin on this table to find the first value of Z. So in other words, here's 1.0, sorry, here's 1.0, there's 1.1, 1.2, all the way to here. There's 1.6 on the Z-axis. Now, if you wanted, say hypothetically, if you wanted 1.62, right, then the values on the margin on the top, on the columns, that's your second decimal. So in other words, 1.6 is here, 1.62 would be here. This is the second decimal, all right? So if you wanted the value that corresponds to 1.62, it'll be this value here. That's what this table tells you. And this value here is the area from 0 to 1.62. But we want the area from 0 to 1.6. So that would be, here's 1.6, and there's no second decimal because it's 1.6 exact. It's not 1.61, it's not 1.62, it's exactly 1.6. So in other words, it's 1.60. So it's the first value in the column with the row being 1.6. So that is the area between 0 and 1.6. So in other words, this area here that I shaded, the size of this area is 0.4452. Okay, all right. So if I had to ask you for the next question, what is the area? What is the area now for this question between 0 and 0.24? What would that be? Using this table. So the same approach that I did before I used 1.6, now I'm asking you, instead of 1.6, use 0.24. What is the size of that area? Can you put it in the chat? Give it a shot. I need to make sure that you're following and you understand the concept. It's very, very important you know how to use this table. Okay, so I'm going to go to the chat. You got the textbook. All right, make a note. You're looking for the area between 0 and 0.24. Write the answer in the chat. I'm getting some answers. Good, good, good. I see people wrote 0.0948. 0.0948. That's what you wrote. And that is the correct answer. Well done. Good, you're following. Excellent. All right. Now I'm going to talk about something called symmetry. It's just a fancy word to say something is a mirror image. All right, I'll explain what I mean by that. Okay, so let me just clear this. And I'll take you through symmetry. right, let me do my sketch. Okay, so we got our bell-shaped curve. Okay, I didn't sketch it great. I'm not happy with the sketch. Give me a second. I want it to look the same on either side of that dashed line, because that's what symmetry is. So I'm drawing it freehand, but obviously the graph, and please give me a second. Okay, that's better. All right. Now, if you look at the graph on the left on your textbook, this is the same graph that I'm drawing. It's centered at 0. Now, I mentioned symmetry. Now, I'll explain exactly what it means. Symmetry means whatever you have on the left of this dashed line, everything here on the left is a mirror image of what you see on the right. Okay, so in other words, if it's centered at 0, then that means we have negative numbers on the left and we have positive numbers on the right. So in other words, say I had negative 0.24 here, negative 0.24 at this line, and I had positive 0.24 here. Then that means that this area, which you worked out, right? You looked at your book and you pulled that area. This area here, which is shaded in green, is exactly the same as the area from negative 0.24 to 0. So it's, in other words, its negative counterpart to 0 will have the same area from 0 to its positive counterpart. So in other words, if this green area is 0.0948, then this area will also be 0.0948. That's what symmetry is. That's all it is. Okay, so in other words now, what the question I asked you before was, what was the area? So the question I asked you before was, what is the area between 0 and 0.24? And you answered 0.0948. So now, using this symmetry, the property of symmetry, what would the area between minus 0.24 and positive 0.24 be? What do you think it would be? That's my question to you. Write the answer in the chat using symmetry. Okay, it doesn't matter if you get it wrong. This is the time to actually get it wrong, so you can work through any confusion, because this is what I'm here for, to help you through that. So what do you think the area is between minus 0.24 and positive 0.24? Nice, very good. Very, very good. So what you did is you added the two up, right? So in other words, the answer is 0.0948 plus 0.0948. In other words, you just added these two areas up, these two. Very good. And that's how you got 0.1896. Very good. Okay, now everything I've done so far, right? I've basically asked you about area, and it seems like you understand that concept. And that's very good, because what you've been doing all this time is you've been finding probabilities. So the first question I actually showed you was, I asked you the area between 0 and 1.6. So in other words, what you solved and what we did there is we actually found the probability that Z lies between 0 and 1.6. That's what we did. Okay, the last question I asked you, this question here, what you actually worked out is you've worked out the probability of z being between minus 0.24 less than z less than 0.24. That's the mathematical notation for being between. All right, that's what you've done. So you've answered probabilities just by working out areas. And that's essentially how you find probabilities for the normal distribution. Now, the question you may ask is, okay, but why do areas give you probabilities? Okay, so now I'm going to connect it to a real world application and how this actually works. So I'm just going to go to the first page. I'm going to check the chat if there's any questions. So far, so good. All right, feel free to ask away. All right, so now what we have, and I'm hoping all of you are familiar with a histogram. All right, so that would have been covered very early in this course. So what this histogram tells you is you have the weights of runners. So these runners, doesn't matter what event they take part, it could be sprinting or long distance, it doesn't really matter. We have 500 runners, okay, we have 500 of them. And what we did is we plotted a histogram of their weights. So in other words, we're showing the distribution of the weights of these runners. Now, what this histogram tells you is that most runners are around 135. Sorry, my bad. There's about 135 runners here that weigh about 70 kg. So your weight is in the horizontal axis here. Okay. You have about 2 runners that are below 50. Okay. You have 11 runners that are between 50 and 55. That's what the histogram tells you. Now, if you look at this histogram, now I'm going to draw a line that basically touches the corners of this histogram. All right, like this. And you'll notice that it begins to look very similar to the curves I've been drawing all this time at the beginning of the session. And that is because this is a normal distribution. It's bell-shaped, right? I used, in this histogram, you've got 10 bins, but if you make the bins smaller and smaller and smaller and very small, like even if you make it like 2 kg intervals, then this histogram will start to look very familiar to a bell-shaped curve. In other words, a normal distribution. Now, if I had to ask you, okay, let me just clear this part here so you can see it a bit clearer. You have 500 runners. 500 runners. Sorry, let me try and clear this. It's there. Okay, so you can see this part here. For the first question, based on this information, take a guess on this, and I want you to try this out, right? For the first question, what percentage of runners are under 55 kgs? So if you look at this graph, you look at the x-axis, so the horizontal axis, there's 55, it's round about here. 55 is there. So the question is, what percentage of runners weigh under 55 kgs for that first question? Remember, you have 500 runners, right? We have in total of 500. So if we want to look at the percentages, it's the number of runners that are under 55 kgs divided by 500 as a percent. So what do you think that value is? 2.6%. Nicely done. Very good. Yeah. Well, look at how many runners are under 55 kgs. That is, you got 2, you got 11. So it's 2 plus 11, which is 13. 13 over 500. All right, that's 2.6%. Let me just check. Excellent. All right. Okay, so everyone follows that. Very good. So what you've actually done is you've worked out the probability that a runner is under 55 kgs. That's what you worked out. So in other words, if X represents the weight of a runner, then what you worked out is the probability that X is under 55. And that is equal to 2.6%. And how did you do that? Well, you actually worked out the area. You see this bar goes up to there. You added the size of this bar to the size of this bar. So you somewhat are working out the area. I know it's not perfect because there's a gap here. I get that, right? But essentially you are working out the area, all right? You're adding up these bars. If I made these bins much smaller, like 2 kgs, like I just said earlier, then you would see that you are working at the area because your bins will be like this. Get it? So that's why working out the area under the curve gives you the probability, right? So that's how you actually apply it to the real world. And that's why the normal distribution is so important, okay? Because this is how you use it in practice. You can work out the probabilities of something if that something follows a normal distribution. All right. Now we are going to solve the next question using a combination of this real world problem as well as the table on the left. Let me just check if there's a chat here. I mean, is the question. So far, so good. Cool. Let's go back here. All right. So you've answered question 1. Very good. Now let's get to question 2. All right. So question 2 says, given that the weight of runners follows a normal distribution. Okay, so we're given this. It follows a normal distribution, which is centered at 70 kgs. Or in other words, the average is 70 kgs. And we can see that, okay? We can see that the average sits around here because it peaks here. And we are given a standard deviation of 7.48 kgs. What is the probability of a runner being above 85 kgs? So in other words, what they're asking us to work out is, what is the probability that X is greater than 85? That's what they're asking us to work out. Now we could roughly estimate it because 85 sits around here, somewhere around here, all right? But we don't need to use this histogram. We can actually get a much more precise answer for this without even using the histogram. As long as they tell us that it follows a normal distribution, and they give us the mean, which they did, and they give us the standard deviation, we don't need this histogram to work it out. We can work out a more exact value for this probability using the table on the left or the table in the back of your book. All right, so let's explain what the standard deviation is. I think everyone knows what the mean is, right? We all know what the average is, and it's also where this graph is centered, in other words, where it peaks. But where does the standard deviation fit in this graph? Well, the standard deviation tells you how spread out the data is. In other words, it tells you roughly how wide it is, right? You don't have to really know where this line sits. The line could be sitting above it or below. That's not so important, right? What is important is it compares it to maybe another distribution of runners, okay? And then it would make more sense. But in this context, the standard deviation, the 7.4, it tells you how wide this histogram is. So if the standard deviation was maybe 10, then this histogram will be a lot more spread out. It'll be fatter, okay? From further left to here to here. That's how the standard deviation affects it, okay? Now, in order to solve this question, right, what we're going to do is we are going to convert this X to a Z value, to a Z variable. So first step is we're going to convert X to Z. And why we want to do that is because the table on your left, that's for a Z variable. And why we need to convert X to Z is because we can't have a table for every single measurement that exists, right? Because if we had to have a measurement for this set of runners, then we also have to have a table for maybe another set of runners from another country, or maybe students that scored certain marks in an exam. Everything has a distribution, and we can't create a table for every single thing. But what we can do is we can convert any table or any data to Z. And once we convert it to Z, to a common variable, then we only need one table to figure out those probabilities. And that's the table on the left, which is in your textbook. So we are going to convert X to Z. And how we do that is we use this formula here. You don't have to memorize it. It's in your formula sheet. So it's Z equals X minus the mean, all divided by the standard deviation. That's the formula. Now, your mean, your mu in that formula is your mean. That's your average. And the sigma is your standard deviation. So that's your standard deviation. So we have all these values. It's in the text. Here's your standard deviation, and there's your mean, 70. Now, the X that we want to convert is this 85. So we want to know what is the equivalent Z value for X 85. So we'll plug 85 into that formula, minus the mean, there's your mean, your average, 70, divided by sigma, which is your standard deviation here, which is 7.84. And that gives you a value of 1.91, I think. Yeah, 1.91. But correct me if I'm wrong, please. So that's your Z value. So that's step one. So what have we done in step one? Okay, so what we're trying to do essentially is we have your runners, okay, which follows a weight of in kgs, which we represent by X. So this is your kgs. It's centered at 70. So here's your normal distribution for the runners in kgs. 85 is on the right of 70, so it's here. And we want to know the probability of X being greater than 75. So in other words, the area on the right of 85. Okay, because X greater than 85 means everything on the right of 85. We want to know this area here. If we can work this area out, then we've solved the problem. That's the answer. But we don't have a table that represents kgs. Okay, so if you check your textbook, you won't see a table that has this graph for kgs. But we do have a table for Z values, which is what you're looking at on the left. So in other words, here, now instead of X, it's Z. And this Z, this variable is centered at 0 instead. And as we said earlier, it goes from minus infinity to infinity. So we got an equivalent shape graph. Right, which the mean of 70 corresponds to 0 for the Z variable. But what does 85 correspond to? And that's what you've done here. Yeah, that's what you've done here. The equivalent of 85 is 1.91. So in other words, it's 1.91 here. All right. So now you can use the table on the left to figure out this area. Okay, so you can work out this area here on the right of it. Now, you've done so far what you've been able to work out is if I told you the area between 0 and 1.91, what would that area be? So you've done it earlier for a different Z value, but now it's between 0 and 1.91. So you use the table on the left to find the area between 0 and 1.91. What is that value? Can you write it in the chat? Very good. Very good. Good. And you found that area to be 0.4719. 0.4719. Right. I'm going to move to the next page. So it's got some space to explain this concept here. And I'll resketch everything we did. All right. So it moves to the next page. I'm going to clear this. All right, so let's sketch that curve again. Okay, so this is your Z variable, centered at 0. And I'll be sketching this curve quite a lot, as you can see, but you're going to have to do this as well when you're actually answering these questions. So it's very good that you understand what these curves are all about. Okay, so here's 1.91. And we were trying to find this area here. But the area that you found, and I'll shade this in green, just so you understand the difference. Okay, so the area you wrote in the chat is this area in the green. Yeah. The area between 0 and 1.91. So this area is what you put in the chat, which is 0.4719. 0.4719. But I want the black area. The black area is the answer. Okay. But how do I use this green area to get the black area? Okay. Let me ask you a question, right? If the areas under the curve represent probabilities, then what does the total area under the curve represent? Remember, area under the curve represents probabilities. What do you think the total area under the curve represents? What value is it? Give it a shot. One effort, one person tried. Okay, does everyone understand that the total area would be 1? It would be 100%. Okay, because remember, from probabilities, your probability cannot be more than 1. It doesn't make sense for a probability to be more than 100%. So the total area under this curve is 100%, right? So the total area, I'll just draw this curve one more time here. The total area, everything, is 100%, right? Now, remember symmetry. If the total area is 100%, then what is this area that I'm going to shade in red? Everything on the left of this vertical line, this dashed line. What do you think this red area is? A lot of colors, I know, sorry, but it's the best way I can kind of distinguish the areas I'm talking about. So what do you think the area in red is? If the total area of the curve, under the curve, is 100%. Hopefully my sketch does justice to you figuring this answer out. And remember, the vertical line at 0 splits this graph into two equal parts. So what is the area in red? Very good. The area is 50%. That's right. Excellent. 50%. So that means the entire area on the right is also 50%. Now, if the entire area on the right of this vertical line is 50%, and you've taken up 0.4719, in other words, 47.19, right? So in other words, this is the same thing as 47.19%, right? Because it's a decimal, so in percentage terms, it's that. Now, if the entire area on the right is 50%, and this green area has taken up 0.4719, or in other words, 47.19%, then do you all understand that the black area is the remaining area of 50%? In other words, this black area here is simply just 50% minus 47.19%. And that's your answer. Because the whole point of solving this question was to figure out the black area. And if you work this out, you get a value of 2.81%. So in other words, the probability of a runner being above 85 kgs is this. That's the answer. That's what you've solved. Does that make sense? Anyone? Is that clear? Does that make sense, everyone? Happy? Okay, thanks. Thank you. Feedback is very, very needed. Okay, so what you've done today is you've determined how to work out probabilities using the table on the back of your book when the problem involves working out the probabilities for a normal distribution, right? You must be able to convert that variable into a Z variable, and then only can you use this table. Okay. It's very, very important that you become comfortable with this. As I said, you will use it in Learning Unit 7 and Learning Unit 8 as well. Okay. I'm going to leave the floor open to you for questions. I will give you some exercises to practice this. Okay. The question, we got 85x when we were working on the history. Okay, let's go back to the histogram. All right, so the second question, let me clear this. I know it's very messy. All right, maybe this makes it a bit easy to read now. The second question, the question says, you are given that the weight of runners follows a normal distribution that is centered at 70. In other words, it has an average of 70. And a standard deviation of 7.84 kgs. And here's the question. What is the probability that a runner is above 85 kgs? So that's how the 85 kgs fits into the question. So in other words, X, this histogram on the X-axis, it represents weights, okay? So that's what your X is. Your X is the weight of a runner. And so what question number 2 asks is to work out what is the probability of X. Now you see the part is being above 85. So in other words, greater than 85 kgs. You have to solve this. Mathematically, that's what the question is asking for you to solve. You are welcome. People, any questions? Is this clear? Does this, anything you're not sure about on this section that I've covered? Okay, I will make the recording available. Thanks, Shakira. Thanks, Danielle. All right, please, if you have questions, now is the time to ask. I will make exercises available, but watch the recording again. And if you do have questions, even with the exercises I give you, please reach out to me and I will assist you. Okay, because like I said, make sure you have this section down really firmly. All right, you must have a good understanding of it. We were done a bit early today, so if you do want to ask any questions, feel free to do so. Otherwise, you can call it. And I appreciate you joining. Thanks, everyone.
Thanks. Bye.
Goodbye. Danae, do you want to ask your question now? I'll stop the recording. Maybe I'll look at your...
That would be great.